Chapter 2 is all going to be about graphing. Specifically in section 2.1, we're going to be graphing sine and cosine functions. When we move into 2.2, we're going to add the additional ones, the other four, all together, so it's a lengthy lesson as well. And then there's going to be some applications of them as we move into chapters or section 3 and section 4. But I want to start with the properties and the details of sine graphs right after the leading idea. So our leading idea is the following. When we look at the graphs of sine and cosine, we see smooth, endless waves, rising and falling, even though we're no longer going to see a triangle or a circle. At first, this might feel disconnected from what we've done before, but this is where faith comes in, not blind belief, but trust in the pattern. And we're going to talk about that in terms of patterns as well. This comes from something. It doesn't just show up out of nowhere. Just as we trust that these waves represent real motion, rhythm, and cycles in the world around us, faith in God asks us to trust His presence and purpose, even when we can't see everything clearly. Like the repeating, consistent waves, God's faithfulness is constant. Over time, what begins as trust grows into a deeper understanding and peace. Let's pray. Dear Heavenly Father, I thank you so much for these students. I thank you for their diligence to be up early, to be in class, and to be ready to learn. I pray that as we move into this new section of material, that I will be able to articulate well the connections from what we've been working with to what we're doing now. I ask that you would help the students today and Monday as we look at this new set of details, that they would make sense. In Jesus' name I pray. Amen. Okay. So there's a lot of writing. If you did not choose to print anything out, you're going to be writing a lot today. This is one of those kinds of lessons. So I'm going to draw the sketch of the graph, and then we're going to talk about how these properties that are listed here connect to the sketch. Sound good? Okay, so if you're looking at this sketch over here, be accurate in your drawing. I want you to mark off 4 units on the right of the y-axis. Just a second, sorry. Okay, there's my tools. I was like, where'd my tools go? All right, there we go. So you're going to mark off 4 spots as equally dispersed as you can, okay? The last spot that I marked is 2 pi. Halfway between, right, the second mark is pi. And then the ones in between that are pi over 2 and 3 pi over 2. Those should feel like familiar values. They're the quadrantal angles from the unit circle. 0, which is our origin, pi over 2, pi, 3 pi over 2, and 2 pi. We're going around the circle, okay? The graph of sine itself starts at the origin. My hand keeps moving things today, like there. And then it has a peak and a valley at 1 and -1, so it's going to go up to 1, back down to the x-axis. It's going to go down to -1, and then back up to the x-axis. And we're going to connect it smoothly. You're going to do better than I do. Something like this. It looks like a wave. Now, let me give you some real-life scenarios and some different contexts of things that do this. So this is kind of a fun little example, not a super serious one, but have you ever seen the pendulum balls where you pull one on one side and you let it go and it bounces to the other side, right? That's happening in a sine, it's called sinusoidal, in a sinusoidal way. The way that this bounces back and forth is a sine. We'll use a serious example. When companies make products that are seasonal in nature, they follow cyclic patterns like this as well. For example, we're about to hit Halloween. Halloween, pumpkins everywhere. We never see pumpkins except for Halloween, pretty much, right? So sales of pumpkins are going to go up at Halloween and fall, and then they're going to go back down all through the year until we go back to Halloween, and they're going to go back up, and then they're going to go back down. And there's lots of things like that. You can think of many of them. Sales of swimsuits, that'd be an example. Now, they don't go negative, right? This would be this graph sort of shifted up with different peaks and different valleys, but it would still be going in a cyclic pattern. Eggnog, can't find it anywhere except Christmas time, right? Hot chocolate, it's a winter thing. People spending money at the marina at the lake in the summer only. People aren't going to the lake and filling their boats up with gas in the winter, right? There's so many things in our lives that are cyclic that follow this kind of a pattern. So let's talk about some of these details and then we're going to fill in, actually let me fill in the chart here first with you, and then we'll talk about those details. This chart is going to be an XY chart, okay? Just like a x-axis, y-axis values. And what we're going to do is we're going to represent values that come from the unit circle. They're the ones I've already plotted on the graph. But so if you think about your unit circle, okay, have it out from your test if you want to look at it. On your unit circle, when we start at an angle of 0, okay? So the graph I'm trying to graph here is y equals sine x. X is my angle that I'm talking about. So thinking unit circle, when I'm at an angle of 0, what is the sine of 0? What is it? It is 0, right? It's the y value. So on my unit circle, I don't have space to draw in a unit circle on the screen. There's just too much going on. But I hope you have yours nearby that you can reference or think through it this way. So that's a 0. We're going to go up to the quadrantal angle, pi over 2. So we're going from the unit circle up to the top of the unit circle now. Okay, so now we're looking at the sine of pi over 2. What is the sine value at the top of my unit circle?
0, 1.
The ordered pair is 0, 1. What's the sine value? It's just 1. Yeah. And then we're going to come all the way over here to pi at 180 degrees. Okay, so we're going to do pi. So we've come from 0 up to pi over 2, and we're over here at pi. What's the sine value over here at pi? 0 again. All right, I'm back on the x-axis. I have no height. Okay, moving around a bit further, we're at 3 pi over 2. So I'm down here at the bottom of my unit circle. What's the sine value at the bottom of my unit circle?
-1.
That's -1. So sine of 3 pi over 2 is -1. And then we're going to go right back to where we started, all the way back to 2 pi. And at 2 pi, what's the sine value? It's 0 again. And hopefully you can see that as we continue to go around our unit circle, we continue to get the same sine values the entire time. They just repeat. It's cyclic. And these are the values that we plotted in the picture. So this one right here, 0, 0, is where we started. This one, pi over 2, 1, is my top value right here. Right? I'll do one more. The pi and the 0 is my value back at the x-axis. And so on and so forth the entire way we go for the unit or for the sine graph. So let's take a look at some of these properties. Okay, so this is the establishing of where this graph comes from. It's a direct relation to the unit circle, where x is the angle and y is the sine value. That's what it is, and it creates this graph. So taking a look at these properties, some of these things you're going to remember from an algebra course you took along the way. I hope you remember what domain and range are. Domain means what available x values do you have? What do you see? So the way I like to think about it is if I started on the far side of the graph, okay, so I'm over here on the left-hand side of my graph, and I'm walking and I'm looking up and down like this, right? Where do I see values? Well, everywhere. There is never a location along the way as I'm walking that I don't look up or down and find a value of my graph. In other words, there's no breaks. There's no jumps. There's no place where I stop and have to sort of like jump over to see another point. You know what I mean? Like it's smooth, right? So I get a domain that includes everything. I have the ability to put any x value inside of sine, any angle value inside of sine, and there's going to be a value that's going to come out. Now, we don't have that for all of our graphs. Do you remember when we were doing tangents and cotangents and even secants and cosecants? There are places where we get values that are undefined. Yeah? The sine doesn't do that. Sine's very friendly. Now, the graph for sine also has a range. So instead of moving left to right along my graph, I'm going to climb a ladder. Okay? So if I'm climbing a ladder, I'm at the bottom of my graph and I'm climbing up my ladder, right? For a long time, there's no picture, right? I'm looking left and right. I don't see anything. Nothing to see. It's boring. There comes a point when I actually see a value for my graph. And the y value where that happens is at -1. That is the lowest y value that I have on my graph, correct? And as I continue climbing up then, I see y values for a while, back and forth. As I'm looking left and right, I see lots of y values. But there comes a point again when I stop and I don't see any more y values. And that point where I stop is at 1. So in some sense, my graph is trapped, right, between the -1 and the 1 values. And that's what the range is representing for us. We talked about this graph being odd before, and we talked about what it meant in terms of an algebraic way, right? Odd meant, and I'll write it down here as a reminder to you, that the sine of negative x is the same as the negative sine of x, right? It was on your test, okay? This is what it looked like. But now I want to establish what an odd graph looks like from a graphical point of view. So I'm going to continue this graph that's already drawn onto the left-hand side of the y-axis. Okay, I'm just going to pattern it over, right? Move it over. So I should be going down. I'm not going to be super precise, but it looks something like that. That's really wonky, but pretend. So let me talk about what odd means from the graph. So from the graph, what odd means is it's like a spinner on a game board. Okay, so you can think, like Monopoly has a spinner. What else has a spinner? Candyland has cards, so that's not one. Life has a spinner. Yes. Monopoly doesn't have a spinner. Life's the one I was actually thinking of. Thank you for fixing that. Monopoly has dice. There's another one. I can't remember if is it Sorry? That doesn't sound right. That has dice. What is it? Twister. Twister has a spinner. Twister's a really good example. I like that one. Okay, so you spin something, right? Well, the idea is that sort of the origin, sort of put the spinner middle in the origin and spin it. And if I spin it around 180 degrees, what happens is, I'm going to keep messing up my graph, is that this piece right here flips down to over here, right? So the blue piece flips to the green piece, and the green piece flips up to the blue piece. But that's actually true for the entire graph. As I spin it, the entire thing spins and lands right back on top of itself. That's what happens when you have an odd function. And you've seen another odd function before in algebra. You've seen probably several, but here's a really good example of one. This one's an odd function. This is y equal x cubed. Same thing, pinpoint in the middle at the origin, spin it 180 degrees, lands right back on itself. That's graphically what it means to be odd, okay? The period is 2 pi. So period in this case is exactly like what we mean, like in a class period in school, right? It repeats. You have your period 1, you have period 2, you have period 3. It's a repeating feature, and in high school or whatever, they're all the same time length, unless you have a weird high school that does them different lengths or whatever. But typically, they're all some weird number, 52 minutes. I don't know why, but there's something like that. There's a repeating piece. So for this, what we're talking about when we say period, and as it applies here, is it's how long it takes before the graph repeats itself, right? So we see the entire graph from the time we start until 2 pi, and at 2 pi, it starts to repeat itself. So it's period. The time it takes for the entire graph to show up is 2 pi. X-intercepts are occurring at every whole pi value, and you can see that pretty quickly. They're at 0, they're at pi, they're at 2 pi, and if the pattern continues, 3 pi and 4 pi and negative 2 pi, right? So they occur at all whole pi values. We have only one y-intercept. That's what functions do. The y-intercept is at the origin, 0, 0. And then it talks about where maximums and minimums occur. Okay, so where do maximums and minimums occur? Well, those are those peaks and valley marks. And if you take a look from the graph, you can see they're occurring at half pi values, right? Which half pi values? Well, some of them are half pi values that look like this, pi over 2 plus 2k pi. The other ones say 3 pi over 2 plus 2k pi. Okay, so what they're talking about here is that the first one shows up at pi over 2. Okay, so look at that. Do you see a maximum over there at pi over 2? Okay, and then 2 pi later, there's going to be another one. And 2 pi later, there's going to be another one. And 2 pi later, there's going to be another one. So this k right here is simply representing, I can do this every 2 pi I want. K is just an integer value. It increases. I can do 2 pi times 1, or I can do 2 pi times 2, or I can do 2 pi times 3, or negative 1, or negative 2, or negative 3. And then the same thing for the minimums. The minimums are starting at the 3 pi over 2. And then they're repeating every 2 pi. That's what this notation means. I don't pretend to tell you that this is friendly notation, but there is no other mathematical notation by which to present this. So that's how they see it, okay? This is how they're going to present it. Okay, that's sines. Are you overwhelmed? Okay, a little bit. Okay, cosine is going to have so many of the same features. You're going to feel like, didn't she just tell me this? But it also has a few things that are different. So let's take a look at cosine. So the graph for cosine, you're going to still mark out 4 units on the right. They're still going to have the same values we had before. So pi over 2 pi, 3 pi over 2, and 2 pi. The difference over here, though, and again, the -1 and 1, that's not different, is going to be where it starts. It's not going to start at the origin. Cosine actually starts at a peak. And then it goes down to the x-axis. And then it goes down to a valley. And then it comes back up to the x-axis. And then it comes back up to a peak. Now, it's really tempting to connect this in a way that just looks like a V. It is not a V. It's got to have that same smoothness that the sine graph did. So it actually connects kind of like this. Kind of like it dips down, but it has this smooth nature on the edges as it opens up. You know, sort of like a flower opening or something like that. Now let's establish where those points came from. They came from the unit circle again. So here's x and here's y. So my x values are still the same ones they had before. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Same x values. And we're thinking about our unit circle, but we're thinking about the cosine values. So I want the cosine of 0. So at 0, right, an angle measure of 0, what's the cosine value? It's 1. All right, what is the cosine value when I get to the top of the unit circle at pi over 2? Yep, that one's 0. How about when I move all the way over here, to the angle pi, same as 180? What's the cosine value? It's -1. And then I move down to the bottom of the unit circle, 3 pi over 2. What's the cosine value? It's 0 again. And then what happens when I get back all the way around to 2 pi? It's 1, and it starts to repeat. Okay? Now, do you remember, this is one that people had a real big trouble with, or at least remembering it on the test, something called cofunctions? Y'all remember it. Yeah, most of you are like, yep, that's the one that I didn't remember which one the pattern was, right? Check it out. I'm going to make one more mark on the left-hand side. It's -pi over 2. And it would be right. Whoops. Sorry, some of these features in GoodNotes are not friendly. Looks like this. I'll erase this in a second. But if I were to restrict my picture here, that's not the one I wanted, here. What does it look like happening between those two blue lines? It should look like it's the graph of sine, doesn't it? So it's like we took one graph and we shifted it a little bit. And how much did we shift it? Pi over 2. That's what came up in those cofunction identities. They're exactly the same values, just shifted pi over 2 from one another. Yeah, so that's how that works. Let me get rid of those blue lines. I will continue my graph in the other direction, though, because I want to mark out a couple other things to establish the values. And they keep repeating, right, just like we saw before. I won't label all of them this time. We'll label all of them on the ones that we're working with more properly. But for the purposes of just being able to see the repeating nature, I'll draw that in. Okay, let's go through properties. Domain. Okay, so domain means, okay, start over here. Domain means I'm walking along the x-axis. I'm starting from the left. I'm moving to the right. Does it make sense that it's all x values? We see all of them. Cool. Range. I'm climbing up the y-axis like a ladder. The first y value I see is at y equal -1. Keep climbing. The last y value I see is at y equal +1. I didn't mention it before, but just as a reminder, those brackets mean we can equal something, like we actually have the ability to equal the 1 and the -1. Parentheses means we can't. We always see parentheses used on negative infinity and positive infinity because those aren't numbers. I can't equal negative infinity. That is not a number, it is a concept. But we also see the parentheses used when we're able to get close to that value and not equal it to. Okay, and that happens sometimes. This graph's an even graph. Okay, so we talked about what that meant from an algebra standpoint. Let me write that in as a reminder. The cosine of negative x is the same thing as the cosine of x. That's the algebra perspective that we saw. What does it mean from a graphical perspective? Well, from a graphical perspective, what it means is that the y-axis, okay, imagine the y-axis there, being a piece of paper that you could fold into pieces. Can you picture that? Okay, so put the y-axis right straight down my head, through my nose, straight down my body, okay? So if I'm even, which most of our bodies are pretty even and they're never perfectly symmetrical, right? It means that if you were to take this and you were to sort of mirror image, like a mirror, you know, like in a fun house or whatever, that the mirror image on the left would be the same as on the right. And in fact, you've probably seen mirrors that flip you around in the mirrors. I've got one in my kitchen in the china cabinet kind of area. It flips my picture around. So when I go like this, my picture over there moves this hand. Do you ever see that? Spoons will do it too. Look in the back of a spoon when you're in the cafe at lunch. Can't remember which direction, but one side of the spoon will actually look the opposite of what your picture is. You have it happen with your cell phones too. There are some apps on your phone that flip you around when you take a picture. And the people who created the cell phones are really smart, so when they do selfies, they automatically do that. Okay, so this happens a lot. So it's an even function because I can split it down the y-axis, and I've got the same picture on the left and right. There's another even function, a very common one that you have seen before, so I want to draw that one in. It looks like this. Does anybody remember what the equation is for this? Don't overthink this. Yeah, x squared. The graph of y equal x squared. You can fold it along the y-axis. It's the same image on the left and on the right. Okay, it feels symmetrical. Not by a rotational perspective, but by a reflection perspective. All right, period is still 2 pi. It takes 2 pi to repeat itself, right? Just like the other one. We have x-intercepts. The x-intercepts are no longer occurring at whole pi values. They're occurring at half pi values. And, they occur at every half pi value. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. They occur at all of the whole pi values, half pi values, for odd pieces. Right? They're not occurring at 2 pi over 2 because 2 pi over 2 simplifies to pi. Right? It's odd pi's over 2. The y-intercept, again, there's only one of them. It's at a peak, 0, 1. I have maximums and minimums. These look a little friendlier than my last screen. The maximums are actually occurring at whole pi values and minimums. But notice we'll do the maximums first. The maximum occurs here at 0. And then it occurs again at 2 pi. So where else is it going to occur? 4 pi and 6 pi and 8 pi. It's all the even pi's, right? So that's what you're getting here. And the minimums are occurring at all the odd ones. They're occurring at pi and 3 pi and 5 pi and 7 pi. Okay, so these are some features of these graphs. Now, there's a couple of pieces of vocabulary that we need as we work through, because you're going to see them show up. Amplitude and period. Now, we've done period before, but let's do amplitude, and then we'll think why period's showing up again. Amplitude is the peaks and the valleys. So on a standard graph, it's -1, 1. We say that the amplitude's 1. It's a distance. It's how far away from the x-axis we go, or from the center of it that we go. But if we have a value in front of sine or cosine that's not, just 1, so it's an a right here, that value a is called the amplitude. And they use a for amplitude to help remind us, so that's friendly. And it simply tells you how far up and down you go. So if that were 3, your peaks and valleys would be 3 and -3. If that were 4/7, your peaks and values would be at 4/7. Okay, that's our amplitude. Period is how far it takes to repeat. Again, the standard period is 2 pi. But what if you actually had a value inside with the x? Well, that's going to change how frequently the period repeats itself. Okay, it's the same thing that's true for some of our products in, life, or how fast something is repeating, right? It changes. So this value b actually takes that 2 pi, right? The one that's the standard value, and it divides it by whatever value is multiplied inside with x. So 2 pi over b is our period. Now we need both of these pieces of information in order to draw an accurate sketch. We get patterns and repeating this, that part we get almost for free. But we need the amplitude to be able to mark the y-axis properly, and we need the period in order to be able to mark the x-axis properly. Okay, one more slide of lots of writing. Are you ready? Okay. This looks like a whole lot. If you have to write it down, I probably would not write it down right now. Just snap yourself a picture like Braden's doing. That's great. Write it down later, fill it in, print those out, whatever. These are guidelines for graphing. All right. So I already mentioned knowing the amplitude and period are really important. And take a look. That's number 1 and number 2. Note the amplitude, right? What is it? What's the peak and the valley? Okay. Second thing is figure out what the period is. Start with 0 on the x-axis to lay out a distance of 2 pi over b. So remember when I started it was 0 and I laid out a distance of 2 pi and then I marked it halfway in between and halfway in between each of those. We're going to do that same thing again, but we're not always going out to 2 pi. So 3 is doing that where we're dividing the interval into 4 equal segments. And then on number 4 where it says evaluate the function as we did in step 2, what that really means is, do I start at 0 and go up, down, up? Like, is that the pattern I'm doing because I'm working with sine? Or am I starting at a peak because I'm working with cosine and then I'm going down, up, right? Establish which function you're working with and figure out what the pattern is so that you can create the graph. Plot those values. And so then on number 5, you in fact do that. You plot the values in a sinusoidal curve. Okay, so this piece right here is telling you it needs to be nice and smooth. These are not V's everywhere or W's everywhere, right? We're looking at nice, smooth curves. And then we draw the graph over additional periods as needed. So typically, you're either going to be asked to draw 1 period or 2 periods. And my math lab has drawing tools for you to do this, by the way. There's going to be a drawing tool. This is one of those sections that may not work very well from your phone if you're using my math lab on your phone. You might need to actually find a laptop. Okay, it doesn't always work from mobile devices for graphing very well. Okay. Is everybody okay to go to actually do one? I don't want to rush, but if you're writing a whole bunch, just snap a picture. It'd be so sad to get to this point and then we didn't actually get a graph anything today. That would be terrible. We'd have to start all over on Monday. Okay, here's an example. Wonderful. This is a very straightforward one. It's not that different from the cosine graph we did before. So how is it different? There's a 2, right? Okay, so in those guidelines for graphing, and it's not like you need to write down step 1 is this, step 2 is this. That's not the point. The point is you're going to cover all of these things, and this is basically the order in which you cover them. So I am going to write down those 2 pieces first, which is the amplitude. So the amplitude is 2. That's the number in front of cosine. And the period is the standard period 2 pi because there's no number multiplied by x inside. Okay, does that make sense for everybody? Cool. Now the direction said identify the amplitude period. We did that, and this says graph 1 period. So we only need 1 period on this one. So we're going to graph like this. It says we're going to mark out the distance for the period. That's 2 pi. And we're going to mark the amplitude height, 2 and -2. Now, if you want to put the 1 and the -1 on there, you can, right? That's fine, just to give yourself some scale. But if you leave them off, it's okay too. They're not the important values any longer. 2 and -2 are. Those need to be listed. Everything else is optional. Now, between the 0 and the 2 pi, I need to divide it into 4 segments. So I divide in half, and I recognize that that's pi. And then I divide those pieces in half, and I recognize that half a pi is pi over 2, and then the other one is 3 pi over 2. That's halfway between pi and 2 pi. Okay, pretty good so far. Getting all the grid set up is usually the thing that makes or breaks you. I mean, it really is. If you don't get the grid set up, nothing else is going to work out. Got to get the grid. Now, I need to evaluate the function. What that means is looking at it and saying, am I dealing with sine or cosine? It's an identification. It's cosine, right? It's cosine. We see that. Well, cosine. Does cosine start at the origin, or does cosine start at a peak or valley?
Peak.
It starts at a peak. So I'm going to do mine in green. My cosine is actually going to start up here at the peak value at 2. Why is it at 2? Because the amplitude's 2, right? What happens to cosine after I start at a peak value? Where do I go next? Yep, I go down to 0. And then where do I go next?
Negative.
Down to -2, all the way to -2. And then where do I go next?
0.
Back up to 0, and then I end at 2. And it looks like a V, right? If you were connecting the dots on, the child's menu at Chili's, you'd probably make this a V. Okay? We know it's not because these graphs have wave type patterns. They're smooth. There's no sharp turns. So when I connect this, it needs to reflect that I'm dealing with something that has a smooth nature to it. And on this one, I'm only asked to graph one period, which means I'm done. Okay? All right, we have time for one more, so we're going to do number 2. What do you notice is different about number 2 that we haven't talked about yet? There is a negative. Any idea what a negative in front might do? It's going to flip the graph. Braden, how do you think it's going to flip it?
Over the x-axis.
Yeah, so it's going to flip it sort of upside down. It flips it top to bottom. That's the kind of flip that we're talking about, okay? So it's a vertical flip. You're vertically flipping it, or you're flipping it over the x-axis. Now, our directions are the same, so we're going to identify the pieces we're asked to. Our amplitude is 3. Notice it's a positive still. Amplitude is always a positive. It's like a distance. Okay, amplitude's a distance, so it's 3. Even though there's a negative problem, it's 3. What's our period? It's still 2 pi because there's still nothing inside with x that's changing that. So I go over to my graph. And I mark that I'm going to be up at 3. I don't usually mark the 2 and the 1 that are missing. I usually just mark the amplitudes, but it's your choice. So I'm going to mark the 3 and the -3. Okay. So that's my amplitude. My period has to go out to 2 pi. And then I divide it into 4 intervals. Pi is halfway. And then I've got pi over 2 and 3 pi over 2. Okay, this is a sine graph, right? It says sine. Where does a sine graph start? At the origin. So if I'm already on the origin, that doesn't flip, right? You can't go anywhere. You're still in the middle where you started. So my graph will still start in the middle. But where does the sine graph typically go after that? Usually it goes up. So what's it going to do this time? It's going to go down. But then what is it going to do? Go back to 0, and then up to 3, and then back to 0. And again, we're not doing this, right? That's not what we got going on. Looks like it, but it's not. We're going to connect it smoothly so that it looks something like that. Okay, so all we've really seen today is the basic graphs, what we do when we change amplitude, and what happens when there's a negative in front. So when we come back next time, we're going to talk about what happens when we do some other things. We're going to change the period, right? Make it more like shorter or longer. We're also going to take the graphs and we're going to like pick them up and shift them. Move them left and right, move them up and down, and see how that looks.